We're now going to move on to the second part of our video. We're going to be looking at the observed reactions in the electrophilic aromatic substitution. So these reactions are going to follow the generalized mechanism, but what we're going to see is that we will change the identity of the electrophile, and therefore the group that is attached at the end will be different. The first reaction is called a halogenation reaction, because the electrophile is going to be a halogen. So what we can do is we can represent the electrophile as either chlorine plus or bromine plus. You'll notice that I put those in quotation marks because the actual electrophile is a little bit more complicated, as we'll discuss below, but effectively it's going to behave as if it were a chlorine plus or bromine plus. This is our observed reaction. We start with our aromatic ring. We use X2 and FeX3. So X2 is just elemental chlorine or elemental bromine, recalling that X is our symbol for halogen. So for example, Cl2 or Br2. FeX3 would be if X is chlorine, FeCl3, if X is bromine, FeBr3. This represents a Lewis acid that we're going to see below, enhances the reactivity of the halogen and allows it to act like an effective electrophile. At the end of the reaction, then we see here that one of the hydrogens has been replaced by whichever halogen we used. If we look at the actual electrophile is a complex formed by reaction of the Lewis acid and the halogen. So if we look right here, Lewis acid is going to have an empty space where it can accept a pair of electrons. So a pair of electrons from the halogen is going to come in, plug into that empty space, and make a bond. This is going to create a negative charge on the iron, a positive formal charge on the first chlorine, which is then going to strongly pull the electrons away from the chlorine on the end. The chlorine on the end will become the electrophile. The aromatic ring will make a bond to that and push out FeX4 minus. The second reaction is the nitration reaction. In the nitration reaction, our electrophile is NO2 plus. The observed reaction looks like this. We start with our benzene ring. We mix it with nitric acid and sulfuric acid, HNO3 and H2SO4. At the end of the reaction, one of the hydrogens will have been replaced by an NO2 group, nitro group. We're not going to discuss the mechanism of how the electrophile is formed in this case. It is actually NO2 plus, which is formed under these conditions, and then it reacts immediately with the ring. One of the useful things about nitration is that the nitro group can be reduced to an NH2 group, okay, which we call an amino group. This can be done using this observed reaction. So we take an aromatic ring with an NO2 attached, react it with tin metal, which we represent as SN0, and hydrochloric acid. This replaces the two oxygens with hydrogens. Whenever you increase the number of bonds to hydrogens from an atom, you are generally reducing that atom. So therefore, we are doing a reduction on the nitro. Our next reaction is going to be sulfonation. Our electrophile is going to be SO3. Now, this observed reaction is complicated by the fact that there are several ways of writing the reagents, which more or less say the same thing, somewhat more or less explicitly. So let's focus first on this one. Technically, what we're going to be doing is reacting the aromatic ring with SO3, which is a gas, dissolved in sulfuric acid, H2SO4. The result will be the SO3 will attach, it will actually gain a negative formal charge, and it will be protonated. So that ultimately we have SO3H attached to the ring. Now, it turns out that Commercially available sulfuric acid actually has SO3 dissolved in it from the manufacturing process. So if we look down here at this reaction, this is the reaction that is used to form sulfuric acid. We take SO3 gas, we mix it with water, it forms an equilibrium, it forms H2SO4. You can see that these atoms, these all add up to the formula of H2SO4. So when we buy commercially available H2SO4, it generally has a slight excess of SO3 in it, which is probably done on purpose in order to suppress the reverse reaction and prevent our H2SO4 from slowly decomposing to make water and SO3 gas. So this would be symbolized as concentrated H2SO4. SO3 dissolved in H2SO4 has also been given the name fuming H2SO4 because the SO3 gas comes out as very potent fumes. So one of these three ways you might encounter one of these three ways of having this reaction written. You can expect on my exams to see it written as I have it in black there so that we're explicit and fully communicating. Sulfonation is interesting because the reverse reaction is also possible. So this is the observed reaction for the reverse reaction. We start with an aromatic ring with an SO3H group on it. We put in dilute H2SO4. So lots of water, small amount of H2SO4, and we heat it. And at the end, what we observe is that the SO3H has come off and it's been replaced with a hydrogen. So in general, what we see is that this reaction is an equilibrium. If we use a high concentration of H2SO4 with lots of SO3, then the hydrogen will be replaced and we will have SO3 attached to the ring. If we use a low concentration of H2SO4 and lots of water, then we'll have a low concentration of SO3 and that's going to cause it to come off and go back to the benzene ring. Our next observed reaction is an extremely useful reaction because it forms a carbon-carbon bond. It allows us to attach carbon groups to an aromatic ring. This is extremely useful in a practical sense because there are a large number of important molecules, especially in areas like medicinal chemistry, where we have aromatic rings with carbon groups attached. Our first one is called the Friedelcrafts alkylation because what we're going to be doing is attaching an alkyl group to the ring. Our electrophile, as we're going to see, is actually a carbocation, which we could abbreviate as R+. The observed reaction looks like this. We start with the benzene ring. We put in RCl, in other words, carbon group with chlorine attached. We would call this an alkyl halide, alkyl chloride. And we put in a Lewis acid like AlCl3, aluminum chloride. At the end of the reaction, what we will see is that the R group from our alkyl halide, the carbon group from our alkyl halide, will have replaced one of the hydrogens. Now we're going to look at this mechanism in slightly more detail because I want to show you how these conditions produce a carbocation. If we look at our alkyl halide, the halogen has a number of lone pairs. The aluminum chloride is a Lewis acid, very similar to what we saw with the iron X3 aluminum acid in a previous reaction. A pair of electrons from the chloride will react and make a bond to the aluminum. This will put a negative formal charge on the aluminum and a positive formal charge on the chlorine. What that's going to do is that's going to create a lot of attraction for the pair of electrons between the carbon group and the chlorine. Chlorine is inherently electronegative, doesn't like having a positive charge. The bond is already polarized toward the chlorine. So the pair of electrons will break away from the carbon group. They will end up on the chlorine. That will leave the carbon group with only 3 bonds. So it will become a carbocation. We will also have a byproduct of AlCl4 negative, which can then react with other things and regenerate the AlCl3. Once we've made the carbocation will react with the aromatic ring by the general mechanism that we talked about before. So the double bond comes out and makes a bond to the carbocation. We get our resonance stabilized intermediate. I'm only drawing one structure, but there would be other structures. Then a base would come. It would remove the hydrogen. A pair of electrons would come down and regenerate the aromatic ring. Now, Friedelcrafts alkylation is not a perfect reaction. There are some problems with it. The first problem is that carbocations rearrange. We already know that from our previous discussions. So if, for example, we were trying to make this molecule right here, this molecule would have an N-propyl group. In other words, a straight chain of 3 carbons attached to it by a primary carbon on the end. If we were to just use N-propyl chloride, so 3 carbons, chlorine attached on the end, AlCl3, we would not get this product. Instead, we would get this. We would have an isopropyl group attached. Why would that happen? Well, because the carbocation intermediate would rearrange. So watch this mechanism. We mix the alkyl halide with the aluminum chloride. The chlorine comes off. We get this carbocation. This carbocation is a primary carbocation. We know that primary carbocations are extremely unstable, and so it would rearrange, moving a hydrogen from the secondary carbon over to the primary carbon, 1,2 hydride shift. We would get a carbocation in the middle, and then that would go on to do our electrophilic aromatic substitution reaction, and the ring would attach to the carbon in the middle. We'll talk about later about ways that we have to get around this. A second problem with this reaction is what's called polyalkylation. Polyalkylation basically refers to having more than one alkyl group attached in a situation where you might want only one. The reason why this occurs is that the product, which is the benzene ring that has one carbon group attached, is more reactive than our plain benzene reactant, for reasons we'll discuss later. So if we were to look at an imaginary situation where we started with 100 molecules of reactant, benzene, 100 molecules of our reagent, we would start with 0 molecules of our product, and we allowed them to react. Halfway through the reaction, we would have expected to use up 50 of the reactants, so we would have only 50 left. We would have used up 50 of the reagents, so we would have only 50 left. And we would have created 50 molecules of the product. The problem would then become that after this point, we would take away one molecule of our reagent, we would make a carbocation. Now the carbocation could either react with one of the 50 molecules of reactant or one of the 50 molecules of product. But as I discussed, the product is more reactive. So it's more likely that instead of reacting with a molecule of reactant, the reagent would react with a molecule of product. So we would get 49 reagents, 49 molecules of product, and 1 molecule of dialkylated. Turns out that it can go in one of multiple places, but we get 1 molecule of this. If you imagine this continuing, this is of course an extreme abstraction, but if you would imagine it continuing that in the next half, only 50% of the reagents reacted with our reactant and the other 50% reacted with our product, we would end up with 25 molecules of our reactant left over, 50 minus 25. We would end up with 25 additional molecules of product, but then we would subtract 25 because 25 of those reacted, and we would get 25 molecules of our dialkylated. So you can see how this would really be a problem. There is a way to get around this. What we can use is a large excess of our initial aromatic ring reactant. In that case, then, there would be such a large excess, so for example, 10 times as much as we needed, we would have 1,000 molecules of reactant and only 100 molecules of reagent. So even 50% of the way through, we would have 950 molecules of reactant, only 50 molecules of reagent, and that of product. And so it would continue to react mostly with the reactant. The third problem is that the carbon atom of the alkyl halide must be sp3 hybridized. We cannot make carbocations from vinyl halides or aryl, in other words, aromatic ring halides, under normal circumstances. So they don't work in the reaction. And so you can see that represented here. If I use vinyl chloride with AlCl3, I would get no reaction because I can't form this carbocation. If I used chlorobenzene under normal conditions, I would get no reaction because I can't form the phenyl carbocation. Finally, Friedelcraft alkylation and our next reaction do not work on rings that contain strong deactivating groups or NH2 groups. This will be further explained below. The last electrophilic aromatic substitution reaction that we're going to look at is the Friedelcrafts acylation. In that reaction, our electrophile is going to be what we call an acylium ion, which I'm going to show below how that is formed and what it looks like. Our observed reaction is going to start with a benzene. We're going to put in this structure, which we could list out as R, in other words, a carbon group, C double bond O, and then a chlorine attached to the C double bond O. That particular functional group is called an acid chloride or sometimes an acyl chloride. We're going to learn more about that later in this semester. We're going to put in a Lewis acid. At the end of the reaction, we will see that the chlorine has been removed. This piece right here, RC double bond OCl, will be attached to the benzene ring. Again, we're going to look at the mechanism of how this is formed. So in our reactant, what we have is what we call an acyl group, RC double bond O, attached to the chlorine. The chlorine will make a bond to the aluminum chloride Lewis acid. Again, that will weaken the bond between the chlorine and the carbon. The pair of electrons will move onto the chlorine, breaking the bond. We will be left with this species right here, RC double bond O, positive charge on the carbon. This is called an acylium ion, which stands for acyl group, IUM, positive charge. This would normally look like an extremely unstable carbocation, but under the circumstances here, it's stabilized by resonance from the adjacent oxygen. So a pair of electrons will move down, creating this. This is probably the major contributor, but we're going to see that the reactive part of it will be this resonance form. Following then our normal general electrophilic aromatic substitution mechanism, the pair of electrons from the benzene ring would come out. It would make a bond to the positively charged carbon. Again, we would lose our aromaticity. A base would remove a hydrogen. A pair of electrons would flow back down into the ring to regenerate the aromatic ring with the acyl group attached. Friedelcrafts acylation avoids two of the problems of alkylation. The first is that the acylium intermediate is resonance stabilized, so it doesn't rearrange. The second is that acyl groups, we will see later, make the rings less reactive, so we don't get polyacylation. However, we do still have problems with Friedelcrafts acylation when we try to do it on rings with deactivating groups or rings with NH2. In particular, the problem with NH2 is that if we were to try to do this reaction on this benzene ring, which has an NH2 group attached, instead of getting products where the acyl group is attached to the benzene ring, shown here, we get products where the acyl group is attached to the nitrogen, because nitrogen itself is also able to react with the acyl chloride electrophile. We're going to talk about this. This makes an amide. We're going to talk about this when we talk about carboxylic acid derivatives in a later chapter. But for right now, we just need to know that it is an undesirable side reaction. Friedelcrafts acylation is extremely useful because it allows us to attach primary alkyl groups to aromatic rings, which we could not do with alkylation because of rearrangement. In order to do this, what we're going to need is another reaction that would convert the C double bond O into a CH2. That reaction is called a Lemenson reduction. It looks like this. We take a molecule that has an aromatic ring attached to a carbonyl, C double bond O. We react it with this reagent, zinc metal dissolved in liquid mercury, which is called zinc amalgam. The mercury is in parentheses because really it represents the state of the zinc as being dissolved in it, just in the same way that we used to write ions, parentheses, aqueous, which meant ion dissolved in water. We're also going to use hydrochloric acid. We can see at the end of the reaction, the oxygen from the double bond O is gone, and instead we have two hydrogens. So it has become a CH2. We're going to go back then and look at how this could be used to attach a primary alkyl group using propyl, which we talked about earlier, as our example. So again, we talked about that if we take a benzene ring and we use N-propyl chloride and aluminum chloride, we would get isopropyl attached. What we can do is we can instead use the corresponding acyl halide or acid chloride. The important thing to note here is that we want 1, 2, 3 carbons attached to our benzene ring. And the first carbon directly attached is going to be a CH2. But when we start, that first carbon will be the C double bond O. So we have to just make sure that the carbonyl carbon plus the rest of the chain adds up to 3. We put that in, we react it with AlCl3 in the benzene ring, we get this. Notice that there are 1, 2, 3 carbons attached, but the first carbon is a C double bond O. We can convert that to our desired CH2 with zinc amalgam and hydrochloric acid, and we get N-propyl attached. So this is a way that we can use these reactions to get around limitations.